Okay. Let's begin as usual. Are there any questions? Yes. I guess Monday. Monday's okay. Is that okay with you? Yeah. Okay. Sure. Okay. Anything else? All right. If not, we were talking about Laplace-Dirichlet transforms. And so I'm starting on page 197. So suppose we have a function f. Then we define the Laplace-Dirichlet transform of the random variable, a distribution function of the random variable x. If I got a better one of these things. By doing the following. I take the differential of the function, I multiply by e to the minus st, I integrate as t runs from 0 to infinity, and I call that the Laplace-Dirichlet transform of the distribution function of x, phi. So that's the Laplace-Dirichlet transform. Note that formally, that's the same thing as the expected value of the random variable e to the minus sx. Okay, to take the expected value of the random variable, I take the values the random variable takes, calling x the dummy variable t, multiplied by the probability that x equals t, and add up over all t. Okay, so Laplace-Dirichlet transforms, what they do is they change the information from one form into another form. And obviously, if you give me the f, I can calculate the phi. But there's a theorem that says that if you give me the phi, I can find the unique f from which it comes. Now, if I have the transform, then I have certain nice properties. For example, if I take the derivative, in fact, let's see, do I want to write all the derivatives? Okay, what I'm writing now is the statement equation 6.3 on page 198. Which is that if I differentiate this thing n times, so I take the nth derivative with respect to s of phi, and then I set s equal to 0, then what I get, as you can see by actually doing it, if I actually simply differentiated this with respect to s, then every time I differentiate, the t comes down here. So if I differentiate n times, then I would get t to the n down here. When I set s equal to 0, the e to the minus st is 1. So I have the integral of t to the n df of t, which is the nth moment. Except for the minus sign, every time I differentiate this, I multiply by minus 1, so the minus signs keep alternating. So the result is that if I multiply this by minus 1 to the n, I get the nth derivative. I get the nth moment. Okay, so that's statement number 1. Here's another statement. Statement number 2 says, suppose that, and by the way, I want to mention that there are analogous properties. These properties are analogous to what we have for the ordinary generating function. Okay, now suppose that we have two random variables, x1, x2, and they're independent. Then the Laplace-Dirichlet transform of the sum is equal to the product of the transforms. So in other words, the difficult operation of convolution in the original space is transformed into the simpler operation of multiplication in transform space. What this means is the following. Suppose that I wanted to calculate the distribution function of the sum. So what I would do is I would take the probability that one of them, say x1, takes the value u, multiplied by the probability that the other one, say x2, is less than t minus u, and then I would sum that. These are non-negative random variables, so that means that I would sum this as u varies from 0 to t. So this is the convolution. That is, if I wanted to find a distribution function of the sum of x1 and x2, then I would have to evaluate this integral. So what the theorem says is that if I actually took the transform of this, so to take the transform, I take the differential of that, I multiply by e to the minus st, I integrate as t runs from 0 to infinity. And now what this says is, now if I did all the arithmetic indicated by this, what I would wind up getting would simply be the product of the integral from 0 to infinity of e to the minus st dfx1 of t times the integral from 0 to infinity of e to the minus st dfx2 of t. So there's a lot of work between here and here, but it's just arithmetic. And of course, what that means is that the left-hand side is, by definition, the transform of the distribution function of the sum, and the right-hand side is the product of the Laplace-Dirichlet transforms of the distribution functions of the individual components. All right, so this is just the same thing that we had with generating functions. In fact, we could prove this more easily by saying that the Laplace-Dirichlet transform of the sum, well, we already said that the Laplace-Dirichlet transform is formally this expected value. So that would be the expected value of little e, e to the minus s, times x1 plus x2. That's the definition of the Laplace-Dirichlet transform. And then I would simply break this exponential into its product. So that would be the expected value of e to the minus s x1 times e to the minus s x2. But then I claim that if we have independence, between x1 and x2, then e to the minus sx1 is a random variable that's independent of the random variable e to the minus sx2. So by a theorem that we all know, although its proof, of course, is basically this proof right here, that the expected value of a product is the product of the expected values if the random variables are independent. So that's the expected value of e to the minus sx1 times the expected value of e to the minus sx2. And of course, that by definition is the product of the transforms, phi x1, phi x2. OK, so that takes care of this very important property. Now, another property, which I think I mentioned earlier, let me mention it again, is that I'll mention up here as property 0, that the Laplace-Dirichlet transform, put it right here, if the random variable x, if its distribution function is differentiable, so that it has a density function, then this can be written as the integral from 0 to infinity of e to the minus st times the derivative of big F, which we traditionally call little f, and this you recognize as what's called the ordinary Laplace transform of little f. Laplace transform of little f. So when we're talking about random variables, if we're talking about the Laplace-Dirichlet transforms of distribution functions, then we find that the Laplace-Dirichlet transform of the distribution function is equal to the Laplace transform of the density function if there is a density function. But if you don't have a density function, you still have a distribution function, so you still have a Laplace-Dirichlet transform. And of course, you have to evaluate this using the stuff about the Riemann-Stieltjes integral that we talked about earlier. Okay, all of this stuff is standard. Now, here's an interesting one that's more special to queuing theory. So here's my property number 3. Suppose that I have some random interval like that, and let me call the random interval, let's suppose that the random interval has distribution function f. So maybe its length is x, let's say, and it has distribution function x. And let's suppose that during this interval, we have customers arriving according to a Poisson process with rate lambda. So the question is to relate the number of arrivals during the interval with the length of the interval. So we're talking about a relationship between the continuous random variable in general, which is the length of the interval, and a discrete random variable, which is the number of arrivals that occur during the interval. And obviously there ought to be some sort of relationship, but it turns out that there's a very simple and useful relationship. So suppose I let Pj be the probability that during this random interval I have exactly j arrivals. Now remember that the interval is random and the arrival process is a Poisson process, and they're independent of each other in the sense that one does not cause the other. But of course, if I have a short interval, then I would expect to have a small number of arrivals. If I have a long interval, I'd expect to have a larger number of arrivals. Okay, but basically, there's the two independent processes that are going on. Okay, now what's the probability that during an interval, this random interval, I have exactly j arrivals? Well, first of all, df of t is the probability that the interval lasts exactly t. And then if it lasts exactly t, the probability that I have exactly j arrivals is lambda t to the j over j factorial e to the minus lambda t. And then if I add up over all possible values of t, from 0 to infinity, then that's the probability that during the interval, whose distribution function is f, I will have exactly j arrivals. Okay, that's not too complicated, but it's an integral relationship. Now, the question is to get another connection between the discrete distribution p and that is the number of arrivals, and x, the length of the interval during which the arrivals occur. And so one way to do that, the way I'm interested in, is to multiply by z to the j and sum over all j and then the left-hand side, of course, by definition, is the generating function. Let's call it little g, evaluated at z. So g of z is the generating function now of the number of the distribution of the number of arrivals that occur during this random interval. Okay, now let's just do some obvious arithmetic with the right-hand side. So what I'll do is I will interchange the order of summation and integration. That always seems to be what you do here. No matter how the problem is originally formulated, the right way is the reverse. So whatever you have, you change it. Okay, so here I have the sum from 0 to infinity inside the integral. Then I will take the z and combine it with the lambda t, so that inside I'm left with lambda t z to the j over j factorial. Here's my e to the minus lambda t, and here is my df x of t. And then I take this sum, and I recognize that that's the same thing as e to the plus lambda tz. So that when I combine things, I have the integral from 0 to infinity of e to the minus lambda times 1 minus z times t df x of t. Or maybe a better way to write it is e to the minus, well, I'll write this out in a minute a different way, slightly different. Notice it's of the form e to the minus something t times df of t. So that means that this, in fact, is the Laplace-Dieltjes transform of the random variable x evaluated when s is equal to lambda minus lambda z. So the conclusion, if you trace through the arithmetic, is that for this process, if the customers arrive according to a Poisson process, and we have an interval of length x, then the generating function of the number of arrivals during the interval is equal to the Laplace-Dieltjes transform of the distribution function of the length of the interval evaluated at lambda minus lambda z. So here's a direct relationship between, simple relationship, between this thing which generates a discrete random variable, which is the number of arrivals, and this thing which represents an interval of time, which could be discrete or could be continuous. So there's a direct relationship between the generating function and the Laplace-Dieltjes transform. It turns out some people actually call this a generalization of Little's theorem, because if I differentiate this, I can get a statement of the form L equals lambda W. Of course, this relates distributions rather than average values, but it's more special because it requires that the arrivals occur according to a Poisson process. All right, so what you're supposed to do is kind of store this in your repertoire of facts, because when we start looking at the MG1Q, all of these things are going to be little pieces that we're going to put together, which are going to allow us to analyze the system. Okay, any questions about these things? This is equation 610 in the textbook. Okay, let me do a couple of these exercises on page 199. The first one says let n be a non-negative integer-valued random variable with distribution function capital F. If phi of s is a Laplace-Dieltjes transform of f, and g is the probability generating function of n, show that something is true. Okay, so what I want to do is I want to relate the generating function and a transform. Okay, so first we have a random variable n that is non-negative integer valued. Okay, so that means that if this is t, if I had to draw the distribution function of the random variable n, then what I would get is something like this. Well, let's say that here's 0, 1, 2, 3, and so on. So the distribution function would look like this. The height of the jump would be the probability the random variable takes the value 0. And then at 1, it would jump again. The amount of the jump would be the probability it takes the value 1. And the height of the graph would be p0 plus p1, and so on. So as long as it's discrete integer valued, it's going to have a graph that's going to look like this. Let's say this is 1 here. And eventually, it's going to get to 1, or at least be asymptotic to 1 if there's an infinite number of values. Okay, now what I want to do is I want to calculate the generating function of the random variable n. So that's equal to the summation of the probability that, let's see, that's the probability that the random variable takes the value j times z to the j, summed over all j. Okay, now let's see. What do we have here? We want to get the probability that what I want to do is I want to take the Laplace-Dietrich transform. I think maybe that's the way to do it. What I'll do is I'll take the Laplace-Dietrich transform of this distribution function. Okay, so here is the Laplace-Dietrich transform of the distribution function of the random variable n evaluated at s. Okay, so that would be the integral from 0 to infinity of e to the minus st df of t. Okay, so now I look at this graph here, and I see that as t moves from 0 to infinity, starting at just to the making sure I contain the origin, that at each point, well, let's see, when I pass the origin, the amount of the jump is p0. Okay, so this would be p0 would be the amount of the jump, and the value of the function would be e to the minus s0. So as t moves from left to right, the first term of this integral is e to the minus s times 0 times p0. As t continues to move from left to right, the differential part is 0. The derivative here is 0 until I get to the next jump point. When I get to the next jump point, the amount of the jump is p1, and the value of the function at that time is e to the minus s times 1, because the jump occurs at 1. Okay, and the next term is going to be e to the minus s times 2, p2, and so on. Which is the same thing as p0 times e to the minus s raised to the 0 power, plus p1 times e to the minus s raised to the 1 power, plus p2 times e to the minus s raised to the 2 power, and so on. So that's at the same form as this. It's the sum of the p's times z to the j, where z is e to the minus s. So therefore, this thing is equal to the generating function with z replaced by e to the minus s. Okay. So in other words, the generating function of this non-negative integer value discrete random variable is related to its Laplace-Dietrich transform of its distribution function according to this simple relationship. The Laplace-Dietrich transform is the generating function, except z is replaced by e to the minus s. So you see that generating functions were defined only for discrete integer valued random variables, whereas Laplace-Dietrich transforms are defined for non-negative random variables in general. And so if you look at a Laplace-Dietrich transform of a random variable for which there is a generating function, the discrete non-negative integer valued case, then you find out that in fact the Laplace-Dietrich transform and the generating function are the same thing. The only difference is a change in the name of the variable. So it's not surprising then that Laplace-Dietrich transforms and generating functions have the same properties, and in fact you can view the generating function as a special case of the Laplace-Dietrich transform. Okay, so putting that together with things like with statements like this, which give you the relationship between the generating function of the number of Poisson arrivals during a random interval and the Laplace-Dietrich transform of the distribution function of the length of the interval, then that means that we're going to be able to go back and forth in our analysis between taking a viewpoint or analyzing from the point of view of a discrete random variable with a generating function, or a continuous, or not in general continuous random variable with a distribution function and a Laplace-Dietrich transform. So that's the reason for doing this. Okay, let's look at exercise number 5 on page 199. Consider again the premise of exercise 4 of chapter 2, which was on page 30, which was this. We already did this one as an exercise for generating functions. So now we're going to generalize a little bit. So I'm on exercise number 5 here. And the idea is that we have a sum of random variables, x1, x2, and so forth up to xn, where n is itself a random variable. So this is a compound sum. And we assume that, okay, now what am I assuming here? I'm going to assume that n has Laplace-Dirichlet transform phi, and that the x's, wait, the n has to be, excuse me. Okay, the n has to be discrete, so I'll assume that n has a generating function g, and I'll assume that the x's, all right, now, earlier what we did is we assumed that the x's themselves were discrete and had a generating function f. And then we showed that the generating function of, let's see, I guess it was, I'll call it f of s sub n of z was equal to the generating function of n evaluated at the generating function of x. Is that correct? Is that what we saw before? Okay, so what we had before was we said, okay, we have a sum of independent, identically distributed random variables in which the number in the sum is itself a random variable, and it has some generating function. And the generating function is g. Okay, so g generates the n, and each of the x's has generating function f. And then we said that the generating function of the sum turns out to be the generating function of n with argument given by the generating function of x. Okay, now I'm going to drop the assumption that the x's are necessarily discrete and have a generating function. But I'm going to assume rather that they are general, and so they have a Laplace-Dirichlet transform. So now I'm going to cross out this assumption, and I'm going to replace that by a Laplace-Dirichlet transform. So now, of course, I can't do that with this because it doesn't make any sense to talk about a number of terms in the sum that's not some non-negative integer. Okay, but here now what I have is a sum of IID random variables in which the number in the sum is random, and the components of the sum themselves are arbitrary random variables. For example, I could have an interval in which a certain number of arrivals occur, and n could be the number of arrivals, and x1 could be the amount of work brought in by arrival number 1, and x2 the amount of work brought in by arrival number 2, and so forth. And I want to know the total amount of work brought in by this random number of arrivals. Okay, so what I'm going to do is I'm going to get exactly the analogous result. Okay, so I'm going to calculate the Laplace-Dirichlet transform of the random variable Sn, or its distribution function, I should say. By definition, that's equal to the integral from 0 to infinity of e to the minus st times the distribution function of Sn, which is the same thing as the distribution or the differential of the probability that S sub n is less than or equal to t. Okay, because that's what I mean by a distribution function. It's the probability that the random variable is less than or equal to t. Once I write that down now, the rest of it's easy. That's going to be the integral from 0 to infinity of e to the minus st. And now I'm going to write the probability that Sn is less than or equal to t just as I did before using the theorem of total probability. So that's equal to the probability that the random variable n takes the value little n, let's say, times the probability that the sum is less than t given that the number of terms in the sum is equal to n, So that means that the subscript here is a little n, because we know this is the conditional probability that this random variable is less than or equal to t, given that the random variable big N takes the value little n times the probability that it takes the value little n, summed over all little n. Okay? And now the rest of it is just arithmetic. All I do is rewrite things. So I'll rewrite this as the sum over n. And that is, I'll take the summation and integration, interchange them. I'll take the probability that n is equal to little n outside the integral sign. Then I'll integrate from 0 to infinity e to the minus st d probability that s sub n is less than or equal to t. Okay, so here I wrote the definition of Laplace-Dirichlet's transform. Here I used the theorem of total probability to rewrite this probability. Here I just interchanged orders of operation. And now I look at this piece right here, and I say, well, what is that? Well, that's the Laplace-Dirichlet's transform of the distribution function of Sn. And what is Sn? Well, Sn for a fixed n is the sum of n of these guys. And we know that the transform of a sum is the product of the transforms. So if the transform of the x's is phi, then the transform of a sum of n of those x's, independent x's, must be the same phi raised to the nth power. So that means that this is the same thing as the sum over little n of the probability that big N equals little n times, I replace this integral by the Laplace-Dirichlet's transform of the x's raised to the nth power, because Sn is the sum of n of them. It's a distribution function of the sum. It's remarkably simple. Okay, now what do I have? Well, remember that big N has generating function g. So this is, in fact, the generating function of g, except that in place of z, I have the Laplace-Dirichlet's transform phi. So this is g of phi of s. Okay, so if I have a sum of independent random variables in which the components of the sum have generating function, have Laplace-Dirichlet's transform phi, and the number of terms in the sum is itself a random variable with generating function g, then the Laplace-Dirichlet's transform of this compound sum is given by the generating function of the number in the sum evaluated at the Laplace-Dirichlet's transform of the components of the sum. So all of this complicated information reduces to the statement here. That transform is equal to that generating function evaluated at transform. And now, of course, if I want to get statements about expected values and moments and all of that, I just differentiate this. And when I differentiate, that means I differentiate this. And of course, I have a function of a function, so I have to use the chain rule. And but I can get all of the moments. So all of this stuff you learned in elementary calculus about differentiating functions of functions, now for the first time, I think it's actually useful in finding something that you really wanted to answer. Okay, so what that does is it says that the exercise 4 on page 30 generalizes and is true, in essence, whether the random variables x are discrete or not. Doesn't matter. All right, so we got all these nice little relationships. Everything seems to be hanging together. Okay, any questions before we... one other thing I should say. I think I erased it here. But one of the properties, of course, we're using it, is the property that the transform of a sum is the product of the transforms. And you know that in your homework problem, I asked you to show, this is part 4 of the homework, you were to define response time as equal to waiting time plus service time. And in that particular problem, you know specifically, explicitly, what the distribution function of W is, what the distribution function of X is, and in the previous homework, you had to take the convolution of those to find the distribution function of R. And this homework problem says, okay, now, take this known result, which you already did by convolution, and take its transform. And then take this transform and this transform and verify that this transform is the product of those two. Okay, so this is just a verification of this convolution theorem with a particular case that you've already done by direct integration. All right, so what that does now is that finishes that chapter, or that section. I'm now up to page 200, starting to talk about a new topic called renewal theory. All right, this is also something that's sort of a review from probability or stochastic processes, and but it turns out to be one of the key elements in queuing theory. In fact, it's going to arise amazingly often. So any questions before I erase this? All right, so right now all you're doing is building up a repertoire of facts from the presumed prior course in stochastic processes. Okay, so here's renewal theory. The idea now is that I have what's called a renewal process, which means that I have these, I can take the viewpoint that these are arrivals. So I could say, okay, here's some time 0. And what I'm going to do is I'm going to imagine that I have arrivals or events or arrows occurring at time t1, t2, t3, and so on, and that the times between these events are IID, independent, identically distributed random variables. So the time from 0 to t1 is x1, and the time between t2 and t1 is x2, and between t3 and t2 is x3, and so on. So in fact, if this is tn here, the arrival time of the nth arrow, then we can say that Sn, we have a sum of these random variables, which is the same as Tn. But I like to go back and forth between Sn and Tn, because when I say Sn, I'm emphasizing that I'm talking about a sum of IID random variables. When I say Tn, I'm talking about the time of the nth arrival. Okay, now suppose we had such a process. And here's the kind of question that we want to ask. Suppose that there's some time, here's the process going on, and there's some time t. And as the process goes on and arrivals occur, then one of these x intervals is going to be cut. That is, in effect, this random t picks out one of those intervals, or another way of looking at it is, as I generate the intervals, then there's going to be one interval that's going to cover the point t. So I can imagine, for example, an arrival process and then some random time at which somebody interrupts this process. And when he interrupts the process, then he generates some other variables. This thing is called r sub t. That's sometimes called the renewal time or the recurrence time, or sometimes called the forward recurrence time. Actually, there are many different names given for it. Equilibrium excess time is another name. You'll get used to the names as we see it in context. Right now, I'm going to call it the forward recurrence time. So the forward recurrence time is the time from t until the next renewal, or the next event, next arrow or arrival. And then there's the time looking backward, sometimes called the age, at time t, and this is sometimes called the backward recurrence time. And then there's the interval itself, which I'll call I of t. That's the covering interval. Okay, so we have this renewal process, which means that these arrows are occurring and the times between arrows are IID random variables, but not necessarily exponential. If they are exponential, then the t's form a Poisson process, but they don't have to be exponential. And what we're interested in is if this process is interrupted, how long is the interval that's interrupted, how long is the time from the interruption till the end of the interval, and how much time has elapsed at the time of the interruption from the beginning of the interval. To put it in context in queuing theory, the reason I'm going to do this is because of things like this. I might have a queuing process. Here's an MG1 queue. Let's say that the server is idle and a customer arrives, and then he makes the server busy for some length of time. And then another customer arrives, and he makes it busy. That is, maybe he arrives here, and then his service time is added on there. And another one arrives, and his service time is added on there, and so forth. So what I'm going to get is I'm going to get a sequence of these service times. And the service times are independent and identically distributed, and they're not necessarily exponential. And now I want to be able to describe the waiting time of an arbitrary customer. So there's two kinds of customers that occur here. One is a customer who arrives when the server is idle, and of course his waiting time is 0 because he enters service immediately. And the other is a customer who arrives when the server is busy. Now, a customer who arrives when the server is busy interrupts a service time. It's just like this process here. That is, this would be the customer's arrival time, and he's interrupting one of these renewal intervals. So the customer interrupts the service time, and then his waiting time depends on the remaining service time of the customer that he interrupted, because he has to wait that long, and then he has to wait in addition for all the other full service times. So the waiting time of a customer in general is a sum of service times. The number of terms in the sum is itself a random variable. And of those terms, one of them is a partial interval, and the others are full intervals. So now you can see how all of this stuff is getting to be tied together. And what I'm talking about here now is I want to understand something about the how much time there is in a partial interval. What's the remaining time from the interruption point until the end of the interval? That's what I want to get at. Okay, now let's, for the sake of argument, just to kind of set the stage here, let's assume that the arrows are going to occur according to a Poisson process. Okay, so assume for the moment, assume for now. Let's suppose that we have a Poisson process. So in fact, we could take the viewpoint that we have an arrival process. So there are the arrivals, and they're occurring. The times between arrivals are IID exponential because we're assuming a Poisson process. And let's suppose that there's some observer, and the observer comes in at random. That's his arrival time. He has nothing to do with this process. And he wants to know how long he has to wait from his arrival time until the next, until the end of the interval, or until the next arrival. In fact, I always like to give this example in terms of what I call taxis. I imagine that these correspond to taxis arriving at a taxi stand. They arrive according to a Poisson process, and this is a person who arrives at the taxi stand to get a taxi. And let's say that the average time between arrivals is 1 hour. So I'm going to take E of x is equal to 1. And what I want to know is, if the average time between taxis is an hour, then when the customer arrives, he has to wait. In general, he's going to arrive between taxis. So he has to wait for the next taxi. So I want to know, on average, how long does he have to wait for the next taxi? And on the average, by how much did he miss the last taxi? And of course, the average value of the age of the interrupted interval plus the average value of the remainder of the interrupted interval must equal the average value of the interval, because the interval is the sum of these two pieces. Okay, so that's the question. So imagine you're simulating this. So you could write a simulation in which what you do is this. Here you have this urn with these tickets in it. And the tickets have the x values. And so you start off and you arbitrarily give some t value. And then you reach into the urn and you pull out these tickets one at a time. And say the first ticket you call x1, and that marks off this amount. And then you check to see whether x1 is beyond t. And if it isn't, you go to the urn and you pull out the next ticket and call that x2. You add that to the value of the last one, and that gives you the next taxi arrival. And you keep on doing that until for the first time you get an x that gives you an arrow to the right of the point t. And then you know, okay, this length of time, that's what you're going to wait for the taxi. That length of time, that's how much you missed the taxi. And this length of time, well, that's the value of x that you just pulled out of the urn on the last trial. Okay, so you got that picture in your mind? Now the question is, if I take, since I'm going to talk about numbers here, I have to make this specific. Let's say, for the sake of argument, that the average time between taxis is an hour. So the question is, on average, how long do I have to wait for a taxi? Anybody know? An hour. Is that right? Were you saying 1 hour? Okay. Okay, if on the average I have to wait an hour for a taxi. Now, why do you say an hour for the average remainder when the average time between taxis is an hour? Okay, the reason you say that is because of the Markov property of the exponential. Because what you say is that since we have a Poisson process, we have exponential inter-arrival times, which means that if I interrupt an interval, the remainder of that interval is independent of the length of time the interval has already lasted, and it's just the same as if I was starting from the beginning. And therefore, if the average time between taxis is an hour, the average time from the interruption to the taxi must be an hour. And in fact, the time from here to here must be exponentially distributed, just as one of the x's is. Okay, how many people agree with that? Everybody? What is that? Well, this is a question. Okay, I think you're getting to the heart of it. But first let me ask this. How many people agree that the average time I'm going to have to wait is going to be 1 hour? It's the Markov property. Actually, there are two reasonable possibilities. If you haven't taken the course, the average time would be 1/2 an hour, because you say, okay, where did I get this I from? I got it from this urn, which means it's one of the x's selected at random. And therefore, since the x's average an hour, then the average time, if I interrupt an x at random, should be 1/2 an hour. So the average time would be 1/2 an hour, but that doesn't seem to be consistent with the Markov property. So the naive point of view is that it's 1/2, and the educated point of view is it's 1. Okay, but now let's take the argument one step further. What about E of A? Well, A and R are statistically identical. From a symmetry point of view, it really doesn't matter whether I look at this thing from left to right or from right to left. Whatever, if I'm arguing that this thing is 1/2 on the average of the whole interval, then if the average value of R is 1, then the average value of A must be 1. But if the average value of R is 1/2, then the average value of A must be 1/2. Okay, so then the question is, yeah, but what about the average value of I? If I take the naive point of view, which of course I know is wrong because it doesn't contain the knowledge of this course, then the average I is the sum of 1/2 plus 1/2, which adds up to 1, which is the same as the average x, which is the obvious correct answer. On the other hand, if I add up the 1 and the 1, I get 2, which is twice the average x, which doesn't seem to make any sense because we know that the I, this covering interval here, this I right here, is one of the x's selected at random. It's just the one that happens to cover this point t. So we have a paradox here, I think. The paradox is that the Markov property says that this column should be right, but if this column is right, then you have to explain why you got 2 for the covering interval and not 1. Okay, so that at first glance seems to be pretty confusing. Okay, does anybody have an explanation for this? Or anybody have a strong choice as to which column you want to choose? I is not random. Right. Okay, so I is not random in the sense that it's a random selection here. I is biased by the fact that you're more likely to pick a long interval. That is, a long interval is more likely to cover this point than a short interval. Okay, so in the case in which we have Poisson arrivals, or the case in which we have exponential times that measure the length of the intervals, then we can understand what's going on. Now suppose that the length of the intervals were not exponential. If they're not exponential, well, the argument that says that the I value is not a unbiased x value, that the I value should still be longer, and therefore the R value should be longer than 1/2 the interval, is still valid, but now you can't evaluate by how much, because the way we evaluated the how much part was by using the Markov property, and in general you don't have a Markov property. Okay, so going back to the queuing theory problem, if I interrupt a service time, then the service time that I've interrupted will be longer. It'll be biased, longer than an ordinary service time, but it's not necessarily going to be twice as long, unless, of course, the service times happen to be exponential. Of course, if the service times are exponential, we don't need this stuff because we already know how to solve the MM1Q. It's the case in which the service times are general. So now what's going to happen is we're going to interrupt the service time, but by virtue of the fact that that service time is interrupted, it's going to be statistically different from all the other service times. And so our job now is to figure out what the properties are of the interrupted service time. How long it is, how much remains, and how much time is left. Okay, so we do that in the context of renewal theory, which has nothing to do with service times. And then we take those results, which are standard in stochastic processes, and apply them to the queuing theory context. Okay, let me write down what the answer is, which is actually given by equation 713. Okay, so here's the answer. Is what I want to get to. The expected value of R sub t. But actually, I'm not really interested in the expected value of the remainder from a specific value of t. As usual in queuing theory, I'll assume that I'm in equilibrium, or in effect that this process has been going on so long, I'm so far away from the origin that, that the finiteness doesn't matter. In fact, I'll take the limit of this as t goes to infinity. Okay, so now we have this process that's not been going on from time 0, but going on from time minus infinity, to say, and I simply take this process that's been going on forever, and I interrupt it at random, and I want to find the expected value of the piece that remains. And the answer is, well, it's equal to the expected value of the length of the interval divided by 2, the naive answer, but multiplied by the factor 1 plus the variance of the x's divided by the square of the average. Okay, so this is one of the important results we want to get. This tells us exactly what the bias is. Notice that if the intervals were constant, if the x's were constant, then the variance would be 0, and then you would get exactly the naive answer. But in fact, you would get the naive answer only if the variance is a 0. So the only time that the naive argument over here, the 1/2, 1/2, would be correct would be in the case in which there is no variation in the lengths of the intervals. So if the intervals have constant values, then your naive intuition would be correct. But in any other case, if there's any variability whatever, then the variance is going to be positive, and there's going to be a bias term. Now, in the particular case of the exponential distribution, it just happens, it's always true, that the variance is equal to the mean square. When the variance is equal to the mean square, that means that this term is 1. That 1 plus 1 adds up to 2. That cancels that 2. And then you find that you get the Markov property, that the average remaining time is equal to the average length of the interval. So in other words, this is consistent with what you have for exponential intervals. But what this formula also does is it tells you exactly what is the effect in cases where the service times, or the intervals, have an arbitrary variance, arbitrary distribution. And that's what we're trying to get at. Okay, so now I got to develop this, this subject, except I'm not going to develop it in detail. I'm just going to try and get to those pieces that are important for our use. Okay, any questions so far? Everybody see this? So I got to prove this. Is the interval independent of the observer? It's assumed in this argument, as you see when I go through the derivation, that this observation point is made without regard to knowledge of this process. But the interval is not independent of the observer in the sense that, like in physics, in a sense, the act of observing affects the interval, because the fact that you have observed this particular interval means that it's biased to be longer than it otherwise would be. So again, it's sort of like the pasta property, or the lack of pasta property, which is that there is the state of the system as seen by the outside observer, and then there's the state of the system as seen by the arriving customers. And they're not necessarily the same thing, even though it's the same system. So the observation, although it doesn't really physically affect the system, it affects the statistics of the system. And that's what's confusing, because in classical physics, when things are affected, there's a physical cause and effect. But here, there's no physical link. There's just a statistical link. And on any individual trial, you can't see it, because you don't know whether what you see is systematic variation or random variation. So that's the essence of probability and queuing theory. That's what makes it interesting and difficult.
It seems that it's related to the Einstein.
What is that?
There is the force diffusion. So EI, obviously EI should be equal to EX if the aberration affect the average.
No, that's not true. It does affect it. In fact, it affects it exactly as indicated right here. What's happening here is that I'm pulling out these values from this urn. And every time I pull one out, then that value is typical in the sense that it has the same distribution statistically as every other. But the one that I'm choosing to call my I is not an arbitrary one. It's the one that happens to cover the point T. And I'm more likely to cover the point T with a long interval than I am with a short interval. In fact, let me give another argument. I've probably given this before, but wouldn't hurt to repeat it. Let me make a extreme example that I think will illustrate this. suppose that we have this urn, and all the numbers in the urn are either 1, half the numbers are 1, and half the numbers are 19. So the average is going to be 10. Okay? All right, now what I'm going to do is this. Now, why do I make it 19? I'm going to make it 99. So the average is going to be 50. Okay, so if I reach in and I pull these guys out, half the time I pull out a 1, half the time I pull out a 99. In the long run, you're going to average 50. Okay, but now, since I realize that I'm in the long run, half of them are going to be 1s and half of them are going to be 99s, in order to, for the purposes of the example, let's suppose that I have them alternate strictly. So it's a deterministic process. So I'll have a 1 and then a 99, and then a 1 and then a 99, and so on. All right, so in the actual process, they don't necessarily occur alternating, but half of them are going to be 99s and half of them are going to be 1s. All right, now take this arbitrary point t. Well, t is selected without regard to the process. I'm going to do that by closing my eyes, walking up to the board, and drawing a line. Okay, so I do that. All right, there we go. Well, I'm 99 times more likely to pick out the big interval than I am to pick out the small interval. So if I'm 99 times more likely, the average length of the interval I pick out is going to be more than 50. It's going to be longer than the average. So what happens here is that the sampling procedure is biased. The way in which I select the interval is partly related to the frequencies with which the intervals occur, but it's also partly related to the lengths of the intervals. Now, if all the intervals have the same length, then everything depends on the frequencies, and your intuition is exactly right. But if the intervals do not have the same length, which means that they don't have a variance of 0, then there's going to be a bias towards the long ones, and your intuition is not going to be right. In the case of exponential intervals, if you have the intuition related to the Markov property, then you can get the right answer. But that means there's still only 2 cases you can handle, namely the exponential and the constant. What renewal theory allows us to do is to handle every case. And this is the answer. And what I have to do is I have to prove that. And there are some other ramifications as well. Okay? Now, it turns out this stuff has been known more or less. I think it sort of came into people's consciousness in a gradual way over the course of recent queuing theory history, running from, say, the 30s, when the Pollaczek-Khinchin formula was first found, up until recent times. I'd say that even though, as we're going to see, that this formula finds itself embedded in queuing theory in surprising ways, ways that you wouldn't expect, but after thought, you recognize that the reason that you see an effect that doesn't seem to make sense is for this reason. But this now everybody understands. I would say that this understanding sort of grew around the 1970s. And by the 1990s, everybody knows it. But in the 1970s, good people were still making mistakes in the literature, getting the wrong answer because they didn't really understand this completely. And prior to that, nobody knew what was going on, and everything was, none of your telephones worked. Well, actually, that's not true. The telephones did work. I never did understand that, what we need all this stuff for. I remember that when I first started working, which was in the 60s, I worked at what is now AT&T Bell Laboratories. Actually, now it's Lucent. They keep on changing their name, screwing up my bio and my resume. I have to keep on writing in parentheses the name of the company what used to be. But in any event, when I first started working there and I was told I was going to be, that this was the greatest industrial research laboratory in the world, and they were working on telephones, and this was in the 60s, and the telephone was invented in 1876, and I had a telephone in my house and it worked fine. I couldn't figure out what we needed all this stuff for. I mean, what was the point? We all had telephones, they worked fine, so what kind of research were they doing? And I figured what the hell they were going to pay me, so I take the job, but I couldn't see what the point was. But that, if you now compare communications in the 90s to what it was in the 60s, amazing things have happened, and probably there'll be equal jumps between in the next 30 years, although I haven't any idea what they could be. I can't imagine. Well, actually, I have my own scheme because I'm a visionary. I'm a theoretician, not an engineer. So if we have engineers in the audience, maybe you can help me out. But my idea is teleportation. And the thing is, what you do is you go into this phone booth like Superman, and you wrap this telephone cable around you, and you dial your number, and you get broken up somehow into little packets. And little packets get sent over the telephone lines, and then they get reassembled to the other end, and you appear in a telephone booth at whatever number you dialed, and the airlines are out of business, and it'll just be AT&T and MCI and Sprint, I guess, taking you, breaking you to packets and putting you together again. So somebody's got to figure out how to do this, and the trick is you can't drop packets now. This is critical. And you got to make sure that when you reassemble the packets, everything is done in the right order, because there could be lots of lawsuits. But once we can get by that little technical difficulty, I could see great things for communications of the future. Okay, so let's get back to renewal theory. So this is our context. Remember, if anybody comes up with some a way to implement my idea, we split this, right? This is we have witnesses here. Okay. First, I'm going to just state some facts. And the first one is equation 7.1. Now, let n of t be the number of renewals in time t. Okay, so we've got this process going on, and here is 0. Here are these renewals, and here's some time t. And first, we're going to talk about how many renewals. A renewal is an arrow. How many renewals there are in time t. And first, I want to calculate the probability that the number of renewals in time t is greater than or equal to little n. And then I'll say, well, that's the same thing as the probability that the sum of the first n renewal intervals is less than or equal to t. This is kind of obvious if you think about it. Okay, so here is t1, t2, and so on. So let's say that here is t sub n. Okay, now t sub n is equal to s sub n. Because I'm defining it two ways. I'm saying S sub n is the sum of the interrenewal times, the sum of the x's, and T sub n is the time of the last renewal. So if the last renewal occurs before little t, that means that the sum of the n renewal intervals must be less than or equal to t. But also, if the nth renewal occurs before t, then the number of renewals in time t must be at least n. Okay, so this event is equivalent to that event, so their probabilities are equal. Actually, a nicer way to write this is to write probability n sub t is greater than or equal to n is equal to the probability that s sub n is less than or equal to t. Because when I use this notation, that is, I write n sub t instead of n of t, then there's a nice symmetry in the way it's written. But in the book, it's written this way. Now, the expected number of renewals in time t. All right, so now I fix a t, and I ask, on the average, how many renewals do I expect to get? How many arrows will I get in time t? And that's called m of t. That's just notation there. Now, this thing is called the renewal function in the literature. So m of t, the renewal function, is the expected number of renewals in time t, from 0 to t. Now we have something called the elementary renewal theorem. And I won't bother to prove it because, again, this isn't a math course, and the result is obvious. It's just what you would expect it to be, which is the following. Suppose I take m of t, the expected or average number of renewals in time t, and divide by t. So I get the average number of renewals per unit time, and I take the limit of that as t goes to infinity. So I get rid of the effect of the origin. So the question is, on average, how many renewals are there per unit time? And the answer is 1 over beta. Now, I didn't define beta, so let me define it right now. Beta, by definition, is the expected value of the time between renewals. Okay, so of course, you would expect that if I divide the number of renewals by the time, I'm going to get the time between renewals, which on average is beta. Okay, so another way to look at that, write this, is to say what this says is that m of t is asymptotically the same as t divided by beta. In other words, for large t, I could say that the average number of renewals in time t is the total time divided by the average time between renewals. So this is what you would intuitively expect would be true. Okay? Okay. Another fact. This is equation 7.5. This is easy to prove. I'll prove it in a minute just by arithmetic. M of t is equal to the sum over j, as j runs from 1 to infinity, of the probability that s sub j, the sum of the first j renewals, is less than or equal to t. Okay, this is a fact that we're going to use. And to prove it, I'll just do some arithmetic. I'm going to calculate the sum as j runs from 1 to infinity of the probability that sj is less than or equal to t. But the probability that sj is less than or equal to t, just replace n by j here, that's the probability that n of t is greater than or equal to j. Okay, so this is then the sum of the probability that the number of renewals in time t is greater than or equal to j as j runs from 1 to infinity. All right, so this is true because of this statement right here, 7.1. Okay, but now I'll simply replace the probability by n of t is greater than or equal to j by the sum of the probability that n of t is equal to k as k runs from j to infinity. Okay? For the number, for n to be greater than or equal to j, that means n is equal to j or j plus 1 or j plus 2 and so forth. And now the next thing to do, of course, is to just write these terms out and see what you're going to get. So I'll write them out. What do I get? When j is equal to 1, I'm going to get the sum from 1 to infinity. So I'm going to get, I'll write it this way. I'm going to get p1 plus p2 plus p3 and so on. So when j is equal to 1, this sum is going to run from 1 to infinity. Okay, now when j is equal to 2, I get this sum running from 2 to infinity. So that's going to give me p2, p3, and so on. When j is equal to 3, I'm going to get the sum running from 3 to infinity, and so on. Okay, so what do I have? Well, if I look at this diagram here, I've got p1 plus 2p2 plus 3p3 and so forth. Okay, so what is that? Well, that's going to be the sum as j runs from 1 to infinity. Maybe rewriting it, the sum is, say, I runs from 1 to infinity of I times p sub I, where P sub I is the probability that n of t is equal to I. Okay, so all I'm doing is in effect interchanging the order of summation. And of course, by definition, that's the expected value. It's the expected value of whatever it is that generates those values, those i's. So that proves it. So this is proving. Let's see, what did I want to prove? I wanted to prove 7.5, right? So since m of t is by definition this expected value, this is definition, and by arithmetic, this sum is this expected value, that proves this. Okay, so that's a true statement. Okay, I only have a little bit of time left, so let me say now what I'm going to do, and then this is where we're going to go next time. Based on the facts that we've generated so far. Okay, what I want to do is I want to find the distribution of the recurrence time. So by definition, the distribution function is the probability that the forward recurrence time is less than or equal to x for every x. And what I want to find is the limit of that as t goes to infinity. And I'm going to give that the name, I'll just call that f of x. Okay, so as t goes to infinity, we're going to get some distribution function. Okay, now, here's our theorem. This is what I want to get to. This is a key result. The distribution function of the time from an arbitrary point until the next renewal is given by 1 over beta integral from 0 to x of 1 minus g of, well, I call it zeta, d zeta. G, remember, is the distribution function of the x's. So the relationship between the distribution function of the times between renewals, the length of the renewal intervals, and the distribution function of the remainder of an interrupted interval is exactly this. That's what I want to prove. Okay, so this is going to be our key result right here. Now, as a check, you could, for example, take the case in which the g is exponential. If you put an exponential in here, then the arithmetic is easy, and you will get exactly the same exponential out here. And that will be another proof of the Markov property. Okay? Okay, so we're going to start here. We're going to prove this next time. And then after that, we're ready to start actually getting into the MG1Q, applying all of this stuff. Okay, so do we have any questions now before we quit? Okay, so see you all next time, whenever that may be. Above the one below it, which of course doesn't say anything, everything lies above the thing below it. And everything lies below the thing above it. But see, that's mathematics for you. It gives you relationships but tells you nothing. Once you understand that, everything becomes easy. So the question now is, I asked you for the case in which n is equal to infinity. Okay, what happens in the infinity case? Well, let's see. Let me redraw this.